Knowledge proofs. Thank you so much, Leo.
Thank you. Thank you for the introduction. Thank you, FOSSASIA and all the people here in Vietnam organizing this amazing event and expanding open source and free software around the world. I've been in free software, open source, like for more than 2 years, and it's an amazing community and a great purpose. So now I'm going to talk about zero knowledge proofs, more from a perspective that is good for like a student of computer science or software engineering. That is like zero knowledge proofs are more kind of commonly talked in the sector of more like cryptography, and the base is cryptography, but has like a software engineering, no? Has a lot of software engineering applications, no? And is starting to get to the general domain of software engineering. We are getting there, although currently most people working in zero knowledge proof are cryptographers. I, as a software engineer, really, that got into this stopped working, or perhaps you need to click on it. Oh. What? Yeah, it was not in the focus of the window. Yeah, no, it's all. Yeah, okay. Because it moved. Okay. So yes, yeah, it's working. Yeah, it's working. No, yeah. Yeah, because so I started working in the PSC, that is kind of like the Department of Internet Foundation that works on zero knowledge. No, I have more like a background in software engineering and kind of like work my way into zero knowledge proof. And I think really zero knowledge proof is already ready for normal software engineering and for like computer science students in the software engineering students to learn it and start kind of building applications with it. And that's kind of like the focus of my presentation about how to understand it from this perspective of the software engineering. It's again, yeah, they lose the focus. Okay. So what is zero knowledge proof? No, if we want to explain it not from like kind of the cryptography that is based on, but like from a point of view of what you can do with it, no? So it's a system that allows you to prove that you know something without giving all the information about it. And so you can also see it if you are applying it to software engineering, no, as a way of proving that I have done a computation. I can prove that I have done a computation from an input to an output without revealing all the information. I can reveal part of the input or not the input or the output or the intermediate values in this computation. No? So that's kind of like what is zero knowledge proof as applied to software engineering. So there is like some examples. I put here some links, so some example to kind of like trying to intuitively kind of understand what is a zero knowledge proof. I will share the slide later, yeah. And this is like kind of like very typical example, okay? So in this case, like Alice is colorblind, okay? And Bob wants to prove to Alice that he can distinguish two balls of that is pink and well, red and blue. So Alice is colorblind and Bob is going to prove to Alice that he can distinguish the colors. So what we do is like Alice kind of like takes the balls and puts them in behind her back, and she chooses whether to swap them or not, and then show them back to Bob, and Bob tell her whether she had swapped them or not. And if we repeat this many times, and Bob is always right, at some point, probabilistically, Alice is sure that both can see the different colors of the balls, but Bob has not revealed to her what is the color of each ball. So there is like this, like privacy, like hiding information, like Bob doesn't have to explain to her which ball is each color, and anyway, Alice gets convinced after repeating this enough time, probabilistically, that the probability that Bob doesn't know which ball is really close to zero. No, there is another example here. I have, for example, here, like you can do, the game like Where is Waldo? Do you know this game? You have like this image, like with a lot of things going on, and there is this character is somewhere here, and the game is to find it. And another example of zero knowledge proof is you can prove that you have found Waldo without telling the other person that you are proving to that, so without telling you what is Waldo. So in this example, you can just like get like a very big piece of paper that is bigger than the Waldo story, and you do a cutout of Waldo, and you put it in front of the paper, and you show Waldo through the cutout. That way, you are proving that you have found Waldo, but because the paper is much bigger than the comic, that way you don't have to, like, the person is not revealing where is Waldo. It's just revealing that knows where is Waldo. So this is the concept of zero knowledge proof, like kind of explained with this physical example. Any questions about this? Everybody understand this? Okay, let's continue. So what is this used for? What is this useful? No, one of the main purposes, the main things that you can use this in software is for privacy. So you can compute things and you don't have to reveal all the information. No? So for example, in blockchain, you can use for privacy in blockchain transactions. Or for example, there is an application that a PSC is working like with the digital ID of India and on Hadar. So you can, for example, generate a proof that you have certain age without revealing the rest of the information of your ID. Then there is scalability. If the computation, if I'm proving that I have computed, like normally, if I tell you, okay, the result of this computation is this. For you to be sure that I'm telling you the truth, you have to compute it again and see if you get the same result. With zero knowledge proof, I can give you a proof that I have computed this and that is the actual result. And probably verifying the zero knowledge proof, it takes less space, like less memory and less computation than the computation I'm proving. So that gives us like the power of scalability. Now that's what like the CK rollups use it for example. And then it can be used also for interoperability. I can prove you facts about a public blockchain, for example, and you can believe me and communicate between systems and between blockchains. Yeah. Then we have like, this is the concept of zero knowledge proofs. And now the kind of like the innovation that is kind of making this kind of being usable in software engineering and for creating applications is the invention of the general proving systems. No? So we have systems that allows you for a general computation to create a zero knowledge proof. Before this, you have to kind of work out for each problem how you can create a zero knowledge proof. No? For example, with a proving system, using a proving system, I can create a proof of bubble sort. So I can create a protocol with this proving system that you can give me an array and I can prove you that I have sorted it with bubble sort. Perhaps sometimes without revealing if I don't want the sorted array or the intermediate values, or for example, for a Sudoku, no, I can create, like using the proving system, a protocol that you give me a Sudoku unsolved, and I can prove to you that I have found the solution of the Sudoku without revealing you all the numbers in the Sudoku. So that's kind of like, everybody understand at this point? You know, yeah, because this is kind of, the idea is to kind of generate more like kind of questions so we can explain the things better. Yeah, okay. Okay. So, so the main misconception, like people, if you already know, heard about zero knowledge proofs from you are studying software, or you are a Web 2 developer, kind of like there is these ideas that you need to do, like you need to know a lot of advanced math to be able to do zero knowledge proofs and to build zero knowledge proofs applications. And I don't think that's true. Now we have more languages on top of proving systems that are kind of helping you immensely. So you don't need really to know the underlying math that zero knowledge proofs are based on. You need this advancement to create the proof systems, but you don't need, in the same way, like someone can learn Python without really knowing how microprocessors work. With this proving system, you need to do this known math to create the proving system that is like the CPU, but you have these kind of things closer to Python, although not that far. That are the proving systems and the languages that allows you to create this zero knowledge proof most easily. No, the very popular known language is CIRCOM, that make it easier to create zero knowledge proof, and we are working in Chiquito at PSC, and there are many other languages that make it more easily to build zero knowledge proofs. There is it's still an obscure sector, like where more people work from cryptography. So everything is explained in cryptography terms yet, and there is not so much kind of education material for software engineers. No, so well, a good source, I think, is Zero Spark. Have a very good couple of tutorials in CIRCOM and Halo2 that are very good. Okay, so what is like when you are building your zero knowledge proof protocol using a proving system? What are, as a software engineer, what are the things you have to consider? Okay, so the first thing is the witness. What we call the witness is kind of all the data about all the data that you are creating the proof about. So the witness, usually if you are thinking we're creating a proof of a computation of algorithm, no, the witness includes the input, the output, but also all the intermediate values that we're doing in the computation. No? And like talking about the zero part of zero knowledge, like some part of the witness is private. So sometimes like we call advice to the private part and instance to the private part. No, but the whole witness in proving system, usually you arbitrarily can choose kind of like what part of the witness is public and what is private. No, so what only the one generating the proof will know. No? Then there is like kind of like the setup or the circuit or the arithmetization. We can call it by a different name, but it's kind of like basically from a higher level point of view, from an application building point of view, is a series of like constraints of assertions on the witness. So we are saying, okay, only the witness that follows this arithmetization, this setup, this circuit are valid. Actually, we are proving that we have done this computation only if this setup matches this witness and is true for this witness. Okay, and then there is the witness generation that is kind of actually the algorithm itself that we are proving that is generating all the witness values. That's like different things you need to consider as a software engineer. Then there is the proving and the validation key. So for the circuit, for the setup, we get two keys that are both publics, no? And the prover having a witness using the proving key can generate a proof, no? And this, but they can generate only a valid proof is if the witness is kind of matches the constraints that we have put in the setup. Okay, this is kind of clear until now, yeah? Yeah, you all know it already? Okay. So the validator is like can get a proof and just with and the public part of the witness, and just with the validation key can check if the proof is valid. So the validator will be sure that the prover has a witness that matches the setup. and that also this witness, like the public part, is this public part. Okay. So I try to explain it here in a very cool diagram. Okay. Okay. So let's see if everyone kind of verify. So we are trying to generate a public, a zero knowledge proof protocol for a specific algorithm. Okay. So what is the developer? The developer kind of like have to build two things, two programs. Okay. Need like the normal, doing normal programming, have to build the witness generation. Okay. And like in what is called like the arithmetization, the setup, the circuit, is going to specify kind of which witnesses are valid, which witnesses are always the result of the algorithm we want to compute. No? The witness contains all the information, including intermediate values, input, output. No? So this arithmetization defines what is valid. No? So for example, for a Sudoku, the delimitation defines what Sudokus are valid Sudokus. No? Okay? And the witness will build the intermediate values to calculate the Sudoku itself and not the intermediate values to calculate the Sudoku. No? And then from this circuit, the setup of the proving system will generate a proving key and a verifying key. Okay? And then this is like the star are kind of executed for different inputs, are executed many times, no? Like each input. So in the case of the Sudoku, let's follow with this case, no? Like the input would be kind of like the unsolved Sudoku. The witness generation would generate like kind of like a solved Sudoku, okay? And then the prover with the solved Sudoku, the proving key can generate a proof, with the public part being the unsolved Sudoku, and the verifier, there is another person, with the verifier can take this proof and be certain that this prover has solved the Sudoku without receiving more information that was made public in the protocol. I don't know if like everyone understand this. So we'll kind of like overview from kind of like a programmer point of view of what they have to do to kind of generate a zero knowledge proof protocol. Yeah. No. Okay. Okay. That's very good. So I have some. This is going very fast. This is the time that is going faster. I have like some example code to show you kind of like how is this in Circom. Okay. So very, very simple example, no? Like the computation we want to prove is like this equation, no? X to the third minus x plus 7 equal y, no? So with the proof system, we can for example prove that we know an x and a y that matches this equation, and then we can depending on how we define the circuit, we can even not reveal x or y, or only reveal y, or only reveal x. No, but like the verifier will be sure that we know a solution. Okay. And this we were talking about witness generation and the kind of the setup part of the circuit part, like and the witness, no? So let's identify a bit here the different parts, no? Like here these that are called signals in Circom. This is kind of the witness, no? So our witness in this circuit has four components: x squared, x cubed, and out. Okay, Ex is an input. Out is an output. Okay, and the rest of the signal are kind of intermediate values, but all of them together are the witness. Okay, and then we need to do the witness generation that is done with the single arrow in Circom. We basically, this program is executed well. Yeah, this program when we're evaluating the witness, this program is executed and the arrows kind of like assign values to the signals, and hence to the whole witness, because x is given in the input. And these are the constraints. These three equals defines the circuit, like what are the what are the possible values that are a valid witness. In this case, they are the same, and in the most simple cases, sometimes they are the same. So that's like there is an operator in circum, there is like the double arrow that does both things at once. But I think it's clear, like, to kind of like show that there is like two different things. This defines which witnesses are valid, and this is one way of generating the witnesses. No, we need to use x squared and x cubed because, like, in circum we cannot have like in one constraint. In this arithmetization, we cannot have more like the power of 2, like more than a degree 2 polynomial. No. So that's a constraint of the arithmetization. So that's why we need x squared, x cubed. But this kind of like what I want to explain, no? This kind of defines, okay, like the x squared, x cubed out, there are valid witnesses, have to follow these rules. And this is a way of generating these values that follow this rule, okay? But there can be other ways, and that's okay. So with this program, with this code on circum, using circum, you basically can do this, no? Like the witness generation and the circuit is kind of in circum is in the same kind of code, no? So the witness generation is the single arrow, and the circuit is the triple equal. And from that, no, you can execute all this. From the circuit, you can create the keys, and then you can do this for all the x. You can execute for all the x. You can execute the witness generation. Well, I mean the single arrow. You can execute for any x. In this case, will be x the input. This generate all the values, the 4 values on the witness. And then the prover could generate proofs that include the part we want to make public, for example, x. No, so we would prove that we know a y that given an x follow the equation, and and then the verifier can be sure that the prover knows the solution of the equations without having to compute the whole equation. So we can imagine, like, if this. Instead of this example, we have like a very complicated, very, very, very hard computation to do, because we can do this like much easier. This can help with the scalability, no? Because I can give you a proof that I have that the final result of this very complicated computation is this one, and you can be certain without having to calculate it again and seeing if I'm telling the truth. And this is one of the ways that is used mostly in blockchain for rollups and L2s and all that. And that's kind of like completed. Thank you very much. And if you have any questions, let me know.
In the circum language, right, there are 2 steps I have to do. I have the witness generation and I have this circuit arithmetization. Yeah. If these 2 statements don't match up, does the compiler like verify that and tell me, or does this blow up in my face at runtime?
No, like you mean if wait, did you go? Okay. You mean if you present a witness that doesn't match the triple equal equations?
Yeah, for example, like I say out is cubed minus x plus 7, right? And below that I say cube out is equal to minus.
Yeah.
The second one, in a second, so up there I say out is cubed minus x plus 7, and down there I say plus 6.
Yes.
What happens?
So you can, so only if you present a witness that follows these equations, you will get a valid proof. So if you change the equations, you will need to present a witness that follows these new equations.
Okay, so me as a programmer, if I make a mistake there, the result will be that the prover will only generate.
The prover will generate an invalid proof. If you present a witness that doesn't follow the equations, the prover will generate an invalid proof.
Okay.
So the verifier will know if it's valid or not. Yeah, if your witness, the verifier will know if your witness matches your circuit because the proof is valid or not.
Okay.
Good. Okay.
Any other question? I have one actually.
Okay.
Do you have examples of zero knowledge use cases or applications that are live today?
Alive?
They're alive, yes.
Yes, like, well, all the Polygon Hermes, Scroll, all the CK rollups, CK Sync. Yeah, that's the one that I'm more familiar with. No, we have Tornado Cache.
So Tornado Cache is for privacy and
Yes,
ZK
and the other-
rollups for
Scalability.
Scalability.
Yeah. Yeah, so that, yeah.
Interesting, thank you. All good. Well, thank you so much, Leo. That was great.